Hey students, welcome to our first lesson for Astronomy Fall 2020. This is the lesson over the celestial sphere. It's the first topic we're touching on this year, getting started right away on our first day of school, Wednesday, August 12th, 2020. And I've started off by having you take a look here at my view of the E-class page. Again, you should have already clicked on the astronomy introductory video and watched that. It'll kind of give you just an idea about who I am, Mr. Nathan Williams, as your teacher, and also get you familiarized with the expectations of the course and also familiarized with the E-class page itself. And I wanted to also go ahead and point out the second link on that announcement is the link to take you to today's lesson and assignment instructions. Now, of course, if you're watching this video, you've probably already gotten there, but just for future reference, if you click on that link, it'll take you to the content page and the file for today's assignment instructions, Wednesday, 8/12/20, introduction and the celestial sphere. And again, you can read over that yourself, but it tells you what to do if you are attending synchronously, which today that would be first period astronomy class, or asynchronously, which would be either second or fourth period astronomy class. And again, you really should be watching this video if you are attending asynchronously. First period should be attending the live version of this lesson via Zoom. All right, so with that said, I'm going to go ahead and open up our PowerPoint, and then I'm actually going to shut off my camera so that you can see the entire screen. You don't have to have my view obscuring anything. And one thing I've done with the lesson for today and the first couple of days, today, tomorrow, and on Monday, is I have an overall PowerPoint just called The Night Sky, and it covers all these first three major topics of the celestial sphere, which again is what we're looking at today, navigating the night sky, which is tomorrow's topic, and then absolute and apparent magnitude, which is what we're looking at on Monday. So there is a PowerPoint that has all three of these topics together, but since we're going to be looking at each of these little subtopics day by day, there are versions of the PowerPoints that are broken apart into these individual topics. And that's what you're looking at here. This is the PowerPoint that's just addressing the celestial sphere lesson. All right, so moving on, here we go. There we are. Okay, so just starting off, again, this is our first day of astronomy class, so maybe we should address what exactly astronomy is. And like it says here, astronomy is the study of the universe. That's how we define the term in our current times, a modern definition. Another word for the universe you see some come up sometimes is cosmos. We can get into where these words come from a little bit later on. But just know if you ever hear that word pop up, cosmos, that's basically a synonym for the universe. That being said, you may not have ever necessarily had the word universe really defined for you. And this is still a pretty general or broad definition, but we would, as astronomers or science in general, would define the universe as all of the matter, energy, time, and space that we know of. So again, matter makes up most things that you're aware of. We also have energy, moving and powering things. Time, of course, is something that allows events to continue to occur moving forward, and space is in the space in which all these things happen and exist. Now, the word astronomy literally means, and this, by the way, when you get into the origin of words, that's a practice called etymology. So that's kind of what we're doing here. We're looking at the etymology of the word astronomy. And it literally means the naming of the stars. Astro is a root meaning star, and then NOM down here at the back end is a root meaning naming. So, and that kind of reflects the history of the field of astronomy. Astronomy is really one of the oldest sciences because its roots go back to the earliest times where people tried to make sense of the night sky above them, and really the daytime sky too. But of course, the night has all of these different stars and planets we can see, aside from just the sun and the moon. So again, the original function, or one of the original functions of astronomy, was identifying and mapping the stars of the night sky, and we still have that reflected in the name we use today. Now, one thing that a fair amount of people still get confused about, even, I talk with educated adults, and sometimes people still get mixed up about this. Astronomy is not, as you can see here, astrology. Now, astrology sounds like a science class, or the name of a field of a science, like biology does or something like that. And the word would literally mean the study of the stars, just like biology means the study of life. However, we use the term astrology, and it has been used, again, for quite a long time, to refer to what we today consider to be a non-scientific practice of using the positions of stars and planets to do things like determine someone's future. Like if you've ever read a daily horoscope, that's an example of that. Determining their personality type based on their zodiacal sign, which the signs of the zodiac are these 12 different constellations that have a particular importance to them. We'll talk a little more about them closer to the end of the lesson. So just make sure you understand going forward that astronomy and astrology are not the same thing. If someone's asking you, well, hey, what classes are you taking this fall? Don't tell them astrology. That's not what we're doing here. All right, moving on. Again, the main idea for today's topic is the celestial sphere. And maybe you've heard that term before, maybe you haven't. But like it says here, it says the complete field of view from all points on Earth is collectively called the celestial sphere. In other words, if you go outside at night and you can see, different things up in the sky, stars, planets, if you get a telescope out, you can see, nebulae and things like that. All of those views that would be possible from any point on the Earth. Here in Grayson, you go all the way down to Antarctica, you go all the way over to somewhere in Asia, wherever, anywhere that the sky can be seen from Earth, all of those different views make up this idea of the celestial sphere. Now, in ancient times, the celestial sphere was actually thought of as a literal object or structure. And in fact, some people even defined it saying that it was made out of crystal. And either way, it was believed to surround the Earth, the sun, the moon, all the planets that they knew of at the time. So it used to be a literal part of what we would call the cosmology of the ancients. In other words, how they structured or understood the universe. And so, of course, while astronomers don't currently believe in that sort of idea behind the celestial sphere, we now use it just as a helpful metaphor and aid when describing the locations of objects as they appear to us in the night sky. It's a very convenient way of talking about where to find things in the sky. Now, so some basic markers, like the 3 basic markers of the celestial sphere to help you kind of get oriented, are really easy to remember because they correspond directly with some markers that we have here on Earth itself. We have the North Celestial Pole, the Celestial South Pole. I guess I should have just said South Celestial Pole there. And then we also have the Celestial Equator. And these are probably exactly what you might think of from their names. The North Celestial Pole is basically just the point in the night sky directly above Earth's North Pole. So if you were to go to the North Pole and look straight up into the night sky, or even the daytime sky too, either way, that you would be looking at what we consider to be the North Celestial Pole of the celestial sphere. Now, one thing that's kind of unique about the North Celestial Pole is that we have a star that almost exactly aligns to that location in the night sky. And of course, that's called the North Star. Most people are familiar with it. Maybe you even already know how to navigate your way around Earth using the North Star at nighttime, because it can help you figure out, which direction north is, and therefore, where any direction is, and you can use that to help you find yourself to a location. So anyway, one thing we want to know about the North Star, though, a lot of people know that name, the North Star, but they don't know really which star it is. Like it has a more specific name, and that's called Polaris, or Polaris, excuse me. Another name or indicator for it is also called Alpha Ursae Minoris. And that's actually, that kind of name there is what we call a Bayer designation, and we're going to talk more about that later on. Like why would we call Polaris Alpha Ursae Minoris? Now, the celestial South Pole is the point in the sky directly above Earth's South Pole. So again, if you go to the opposite cold place. If you go to Antarctica, directly at the South Pole, and look up into the sky, and of course in this image that's upside down, you would be looking straight at the celestial South Pole. The celestial equator is basically, if you were to go anywhere on the equator, whether it's on land or on a boat at sea, if you looked up, you would be looking at one of the various many points along the celestial equator. And if you, for example, if you could travel all along the Earth's equator, again, by ship or by land, you could just keep tracing visually the celestial equator in the night sky above you, again, or in the daytime sky. All right, so a little more here. As the Earth rotates at night, all stars seem to move around the sky except for what we talked about, Polaris, as it is very close to the celestial North Pole. And that's what this image here is showing. It's this is a time-lapse photography image showing how it's basically collecting light. I'm sorry, yeah, I shouldn't say time-lapse. It's extended exposure. That's what it is. And basically, it's a camera leaving its aperture open for a couple of hours, taking in light from these stars as they appear to move around the night sky. And again, that apparent motion is really due to the rotation of the Earth itself around its own axis. But the reason why you have all these different circular paths, or let me say it this way, the star around which these circular paths gather is Polaris. So even if you perform one of these kinds of photographs, if you try to produce them, Polaris will seem to not move at all. It'll be pretty much a solid point in the image, while all the other stars form these semicircular paths. Now, one other thing, we talked briefly about the celestial South Pole. The closest thing to a south star or southern star is Sigma Draconis, which is a pretty cool name, but it's not really that close to the celestial South Pole by comparison to how close Polaris is to the celestial North Pole. So you really wouldn't get this same kind of effect. And it's not, we're so far away from the South Pole here in Georgia that we can't even see Sigma Draconis in the night sky. But if you were to go to somewhere in the southern hemisphere, you could find it, but it wouldn't be as useful for navigation like the North Star Polaris is. All right, one other thing we kind of need to address before we move on, talking about the North Star, is that a lot of people don't know this, is that the North Star is not always the North Star. And what I mean is that, again, we said that the North Star is a star called Polaris, or again, Alpha Ursae Minoris. But that's not always the case. The Earth's rotational axis, what we would consider to be North Pole on the map, and the South Pole as well, it actually ends up pointing to different locations in space over time. And it takes a while to change. This is not something that's gonna, affect you during your lifetime. But over thousands of years, the North Pole ends up pointing, again, in basically sort of a circular pattern, and there are a few different stars that align with this path. Again, clearly Polaris is one of them because that's where it points to now. However, there are two other main stars that align quite well with this path, and those would be Vega, which is a very well-known star. It's one of the brightest stars of the night sky. Pretty easy to locate, and we'll talk more about it in another lesson next week. But another one's called Thuban, which not so well known, but also a fairly bright star. Now, the term, I kind of glossed over this, the term for this movement of the Earth's rotational axis is called precession. So again, we say that it precesses over time. That's the term. Not procession or anything, but precession. You can see the word here, or at least this version of the word. The overall length of this cycle, so from let's say like right now, again, the North Pole is pointing at Polaris. If we wanted to wait for the entire period of time it would take to go around this entire precessional loop and then come back and point to Polaris again, the whole cycle would be 26,000 years, which is a long time. Written human history doesn't really go back that far, for example. The earliest records we have of written language are about 10,000 or so years old. So for human experience, this is a pretty long time. Now, of course, we'll see later in the school year that with astronomy, we deal with extremely long amounts of time. This will actually be pretty short by comparison. Now, while currently Polaris is where the North Pole points, in about another 12,000 years, the North Pole will align with Vega. So it's going to take about that long for us to have another new North Star. And there will be some time in between there where the North Pole will not point to a particular star, kind of like how the South Pole doesn't really now. Again, the closest thing is Sigma Draconis. The most recent North Star was Thuban, but that was about 5,000 years ago. All right, moving on. Again, some other important things to mark on the celestial sphere. We have the basics of the celestial equator and the celestial north and south poles. One other thing that a lot of folks might mistake for the celestial equator is this new concept we call the ecliptic, or sometimes we call it the ecliptic plane. And what the ecliptic is, it comes from the fact that over the course of an entire year, the Earth revolves around the sun. Of course, you know this. It takes about 365 days, and it makes a complete near circular path or orbit. And from the perspective of us here on Earth, what this means is that the sun appears to make a path through the sky over the course of the year. In other words, if I compare the sun's daytime position to what stars should be behind it, again, we can't see the stars during the day typically just because the sun's so much brighter. But if I do that, then I can see that the sun's position compared to background stars changes over the course of the year. And so it makes this path as it goes in front of different background stars. And that path, again, is called the ecliptic. Now, the reason why it's called the ecliptic is actually, again, a lot of people don't realize this either, although it makes a lot of sense, is that the ecliptic, again, we can think about it as a path, but also as a flat plane. And if we want to have an eclipse, either a solar or a lunar eclipse, then the Earth, the sun, and the moon all have to be aligned on the ecliptic. And again, we'll talk later on in this fall about the mechanics and arrangements that can cause eclipses, but they don't happen unless all three, the Earth, sun, and moon, are aligned on the ecliptic somehow. All right, so we can use this path to make an imaginary flat plane that extends outward from Earth, like the celestial equator, but at a different angle, to match all the points that the sun occupies in the sky over the course of a year. And again, we said this is called the ecliptic plane. Now, I mentioned a different angle. It's actually a specific angle. The celestial equator and the ecliptic, they do intersect at 2 points. And because of that intersection, they form an angle between each other of 23.5 degrees. You can see that marked here on the image. And you see some other terms here. You see summer solstice and winter solstice. We're going to be talking about those right now. Well, almost. We have 2 others first. So the ecliptic and the celestial equator together contain 4 notable locations that occur during each of the 4 seasons. And the first ones, again, that we're going to talk about are the ones I didn't mention yet. These are called the equinoxes. And that's a term, you know the root equi, like equity or equal, means the same. And so nox is a term meaning night. So these terms, or this term, equinox, means equal night. That's the literal translation, basically. But the equinoxes, and there's two of these per year, occur where the celestial equator and the ecliptic intersect. And you can, again, if you look at this diagram, you can see these 2 points. Here's the autumnal equinox, where the 2 intersect, and here's the vernal equinox, where the 2 intersect on the opposite side of Earth's orbit around the sun. So these are the days during the year when daytime and nighttime are closest to being equal in terms of daylight. Nothing changes, of course, about the clock or anything. We don't literally add hours to the day, but we do get more daylight during some days versus nighttime. And the equinoxes are going to be the days where that's the least obvious. The amount of sunlight you get during an equinox is going to be almost exactly 12 hours versus nighttime, which will be, again, about 12 hours as well. So, and the reason for this is because these are the points in Earth's orbit during, again, a year where the Earth's axis is least tilted away from a direct path of sunlight. And we'll get more into that in a moment, because this also is related to the seasons, as you can kind of tell. We're talking about some different seasons here. So the vernal, which is another term for spring, the vernal or spring equinox occurs around March 20th. It's not always on March 20th, but that's a pretty standard date. It can be like the 19th or the 21st sometimes. And the autumnal, or autumnal is what it looks like, but that's how you'd say it, as autumnal. That's the fall equinox. That occurs around September 22nd. And again, that's going to be the next one of these special dates coming up, because we're doing this lesson in August 2020. So the equinoxes, or equinoxes, are also the dates at which the sun will be at its most average height in the daytime sky. In other words, it will not be at its maximum height, nor will it be near its minimum height. It'll be kind of between them. And I have a diagram coming up that'll kind of show you the difference between those points. All right, so we have the equinoxes, which occur again during fall or autumn, and also in spring. But then we also have two events that occur during winter and summer, and those are the solstices. And of course, actually, I say of course. Anyway, solstice, what it literally means, sol means sun. That's actually the proper name for the sun in astronomy, is sol, S-O-L. And solstice means the stopping of the sun. And there's a reason for that. It's we'll get to that in a second. But these two solstices are the locations, again, in Earth's orbit around the sun, where the ecliptic plane is the farthest it can get from the celestial equator. So you can see one over here, or sorry, right here. Here's the winter solstice, and that's showing the ecliptic being pretty far from the celestial equator. And then the same thing over here, but during summer. So these are the times where the sun is at the highest in the summer solstice point and the lowest winter solstice point in the sky. The summer solstice is around June 22nd, so that's the most recent of these four special dates, and is the longest day of the year, again, in terms of daylight. So if you ever keep up with the news, and especially weather and all that, they'll usually talk about that. They'll say, it's the longest day of the year, or they might say it's the first day of summer, all that kind of stuff. All right, so the winter solstice is around December 22nd and is the shortest day of the year in terms of daylight. It's just the exact opposite. All right, so again, I really like this diagram. I think it kind of puts these in a very simple, understandable fashion in terms of what you could see on these dates. So again, the winter solstice, which again is around December 21st or 22nd, that's when the sun will reach its lowest point in the daytime sky. And so if I were in Washington, D.C., looking south toward the Washington Monument, the sun would be well below the top of the Washington Monument. It'd be almost halfway down. And again, that would be at the highest point in the sky, what we call solar noon. On the other hand, if I were to come back either in March around the 21st or in September around the 23rd, again, I would see the sun would be just above the top of the Washington Monument. And again, this is that average height. And again, notice it says March and September, that's spring and fall. This is the position the sun would be in on the vernal equinox and autumnal equinox. Both of them, in terms of what you can see, would be about the same. All right, and of course, the highest point, you can see here it says June, that's for that summer solstice. Again, it's the opposite scenario compared to the winter solstice. And so that's when the sun will get to its highest point in the sky during what we call solar noon on that date. All right, so again, we've been talking about seasons a little bit. One thing that I think you probably already understand, but we just want to address it real quick just to make sure, is why we have seasons, because it is something that does relate, of course, to astronomy. It's not something that just happens on Earth, because of the Earth by itself. It's an interplay between the Earth and the sun. So noticing that the solstices and equinoxes are each named after a season, astronomy helps explain why the Earth has different seasons of the year. The angle that we mentioned that separates the ecliptic and the celestial equator of 23.5 degrees, it's caused by something we call axial misalignment. In other words, the rotational axis of the Earth, which again, that's that white dashed line here in the diagram, is not perpendicular to the ecliptic. And again, don't forget the ecliptic is that path that the sun appears to take over the course of a year in the sky. So in other words, the ecliptic and the rotational axis of the Earth don't form a right angle. If they did, we would not have seasons, because over the course of the Earth orbiting the sun, both the north and the south hemispheres would receive an equal amount of heating throughout the entire year, and we just wouldn't have these differences. But since the Earth is rotating only 23.5 degrees away from the ecliptic, not 90, both of the hemispheres get unevenly heated over the course of a full year. And of course, 1 year being equal to one complete orbit or revolution around the sun. All right, so the changes in temperature we associate with the seasons, especially winter and summer, because they're the more extreme seasons, is due to how direct or indirect sunlight is during each season. During summer, we've got that here in this diagram and also right here. During summer in the northern hemisphere anyway, of course that's where we live above the equator here in Georgia, sunlight shines down nearly directly. You can see that in this diagram or in this one, heating the air, the ground, the water much more easily than in winter when the sunlight is shining onto the northern hemisphere at a shallower angle. And again, you can see over here why that is. When it's winter in the northern hemisphere, the North Pole is tilted away from the sun. So on average, any location in the northern hemisphere during wintertime is still going to get a little bit less sunlight per square meter of ground or cubic meter of air or something like that. During the summertime, that's reversed. The northern hemisphere for us points toward the sun during the summer, and that means that every square meter of ground, every cubic meter of air gets a lot more energy from the sun passing through it. So autumn and spring, of course, they're the more median seasons for the temperate areas. They allow sunlight to cover both hemispheres a little more equally, so median temperatures are more common everywhere. Now, keep in mind, I've kind of been talking about this from our perspective as people who live in a temperate zone of the northern hemisphere. Different areas of the world get a little bit different experience based on how far they are or how close they are to the equator. So, like it says here, keep in mind that equatorial or tropical areas always get direct or nearly direct sunlight. So they typically alternate not between the 4 seasons we've been talking about, but basically just 2 main seasons, rainy seasons and dry seasons. And you've probably read about that, learning about some different tropical areas. Maybe you even know some folks who live there, or maybe you're from there yourself. And so maybe you have some experience with that. But again, here in Georgia or any other temperate region, both in the northern and in the southern hemispheres, we get those typical seasons that we think of spring, summer, fall, and winter. And of course, the opposite of the tropical areas are the polar areas, and they're totally different, right? They're cold all the time, even when they're in their summertime. The summer is very brief. During the winter, some of the and you can kind of tell again. Like, let's look just right over here at this part of the diagram. The North Pole during winter is pointing away from the sun so much that if you're directly at the North Pole, you don't really get sunlight even during the daytime. And that's a pretty cool phenomenon. You should check out some videos about that if you've never really been aware of that. But it also, of course, makes it really cold. So that's when you see a lot of the ice caps develop either at the North Pole during its winter or at Antarctica during its winter. Okay, a little more here. Constellations and asterisms. Everybody knows about constellations pretty much, but again, maybe you don't know, why they're called constellations, or why, maybe you don't know too much about them in terms of detail. Unfortunately, this is one of the topics that a lot of people think of when you think of astronomy, but it's something that we just don't really, like the AKS doesn't really bring it up too much, so we're not going to spend too much time on it. But constellation, and I don't really have this typed out here, but the word constellation literally means stars together. CON is a root or a prefix, means together, and then stel is another root meaning star, kind of like astro also does. But what they are, constellations are stars that humans have grouped into recognizable patterns. And while this is an ancient practice rooted in navigation, agriculture, and entertainment, in other words, like it says here, you couldn't watch movies or anything in 8000 BC. One reason why people came up with a lot of different constellations is because at night, that's one of the few things they had to do. You could just look up at the stars and kind of make up stories about what you saw in these patterns. Like here, we've got the constellation of Sirius, or I'm sorry, of Canis Major, with Sirius as the bright star there. And a lot of cultures have interpreted that as a dog. So anyway, a body, an organization called the International Astronomical Union, the IAU, they now recognize 88 official constellations, many of which are familiar. like Sagittarius, Ursa Major, and Orion. You've probably heard of those. So most of the northern constellations, so constellations you can easily see from here in the northern hemisphere, that's what we mean there, they date back to ancient times, but since European astronomers did not journey to the southern hemisphere until a few centuries ago, many of the southern constellations that you can see from the southern hemisphere are named for more modern things like microscopes, compasses, and so on, rather than mythological characters, things like that. However, there are many more unofficial constellations from various cultures. For example, the star Altair is part of the constellation Aquila, the eagle, but to the ancient Egyptians, Altair was part of their constellation called the Giant. And there's a link in here. You know, of course, if you're watching the video, you can't click on the link necessarily, but if you view the PowerPoint on your own, you can find that link. And this is a great website for looking at how different cultures have interpreted patterns involving the same stars. You really should check it out. It's pretty cool. Now, a similar idea to a constellation is something we call an asterism. And actually, a lot of quote unquote constellations you might know might actually be asterisms. And the most famous example of that is the Big Dipper. And you can see that this little animation I have over here shows you how what most people recognize as the Big Dipper it looks like it could be a constellation, but since it's actually part of the larger Ursa Major or Big Bear constellation, it's really considered to be an asterism. And so what do we mean by that? Well, first of all, an asterism is not going to be one of the 88 official constellations recognized by the IAU. So that's part of it. But also, asterisms are usually going to be either one of two things. They're either going to be part of a larger existing constellation, and the Big Dipper is a really good example of that, or they might be kind of the opposite. They might be a larger pattern that uses stars that are parts of multiple different constellations. And a good simple example of that is the summer triangle. Which is just exactly what it sounds like. It's a triangle of stars that can be viewed typically during the summer months. So right now is a good time. And the stars that make up its points are Vega, Altair, and Deneb, and each one of those belongs to a different constellation. Vega belongs to Lyra, Altair, we've already said, belongs to Aquila, and Deneb belongs to Cygnus. So again, a lot of recognizable patterns that you may know of might in fact be asterisms, as opposed to being officially constellations. All right, we have the zodiac, and yeah, this is our last bit of information for today. The zodiac is, again, another thing a lot of people are familiar with. And so we have this collection of constellations that intersect the ecliptic. In other words, that path that the sun appears to take across the sky over the course of the year. When I was describing it earlier and I said the sun could appear in front of certain background stars, these are those background stars, the different constellations of the zodiac. Now, the zodiac, of course, is something that astrologers are very, very focused on. It's a very important idea to them because basically, so like for example, if you're born during a time in which the sun is in front of, let's say, Sagittarius, then that becomes your zodiacal sign, quote unquote. And that determines certain things about you, at least according to the tenets of astrology. However, one other thing that we'll mention here is that, again, astrology really only officially recognizes 12 constellations of the zodiac when, in fact, there's really 13 of them. And I'll go ahead and point out the one that's usually left out. Not usually, it is left out by astrologers, and it's called Ophiuchus. And it means the serpent bearer. It's right here on the diagram, and when we say the serpent bearer, it's a guy holding a serpent or fighting a serpent, and that's what the constellation represents. But again, it's historically been ignored by astrologers. Although, I mean, you can't really argue that the sun doesn't cross its path. So, from an astronomical perspective, a scientific perspective, it definitely would belong to the zodiac. And so, again, here are the 13 total groups or constellations of the zodiac. Of course, Aries, we have the ram, just like we're rams here at Grayson, and you can see it over here. Taurus, the bull, which is a very easy to spot in the sky. It's close to Orion, which is a very recognizable constellation. Gemini being the twins, Cancer, the crab, Leo, the lion, Virgo, the young women, woman or virgin. Of course, that's what it literally means. Libra, the weighing scales. Scorpius or Scorpio, the scorpion. It's a pretty easy one to figure out. Again, we've mentioned Ophiuchus. And then we have Sagittarius, which that's kind of an interesting one because Sagittarius, the word itself just means archer. Like sagitta means arrow in Greek. But it's not just an archer, it's an archer who also happens to be a centaur, a half man, half horse. So that's kind of fun. That's kind of exciting. Another kind of weird one is Capricorn or Capricornus, the sea goat. It's kind of like a mermaid, but the goat version. You know, the front half's a goat, the back half's a fish. Then we have Aquarius, the water bearer, and by that, again, we just mean someone who's carrying. It's usually depicted as a male youth who's carrying like a large jar of water. And then we have Pisces, which are two fish linked together by a band or a ribbon or what have you. Now, one thing that's important to know about the zodiac signs, especially as it relates to astrology, is that the association of particular constellations with birth dates is actually really out of date. In other words, if you have looked up what your sign is, then that would only really have been accurate about 3,000 years ago. That's when ancient Babylonian astronomers kind of set these dates in stone, as it were. And there's been enough time that has passed since they've done that the Earth's North Pole, its rotational axis, has precessed, like we talked about earlier, about 30 degrees off from where it was when they kind of came up with this system. And what that means now, like just a practical example, the traditional Libra dates that the ancient Babylonians set up are from September 22nd to October 22nd. However, if you actually want to be born when Libra is in the sky, aligning with the sun, nowadays that actually happens much later. It starts on October 30th and ends around November 23rd. So pretty different. It's shifted almost by a whole month. So you can see why, again, there's not, this is just one way in which, again, astrology is kind of described as a non-scientific practice. But again, sometimes it's just kind of fun to think about that sort of stuff. All right, and that is the end of our lesson on the celestial sphere. Thank you for joining me. Again, make sure you go to work on the assignments that are associated with this, and I will see you tomorrow.